Привет, Саша. Спасибо, что пришел.
Здравствуйте, Арина.
Так,
Здравствуйте.
я, оказывается, рассылал какую-то неправильную ссылку всем вот здесь сейчас. Попробую это исправить.
О, Линель, hi.
Так, сейчас я... Ага, ну все. Вроде бы уже можно даже и начинать.
Тогда я экраном попробую поделиться. Вы скажите, что все видно. Вернее, видно ли.
Да, значит, у нас сегодня выступает многолетний участник нашего семинара, которая начала еще в статусе студента, а теперь уже в качестве соискателя для защиты диссертации. Давайте, Арина.
Recording in progress.
Которую я под такой фамилией не очень хорошо знаю. А как вас произносить? Скажите, пожалуйста.
Voorhaar.
Voorhaar. Ньютон, многогранники Ньютона, и все там связано с
разреженные
особенностями. А вы будете говорить по-русски или по-английски?
No, I'll speak English because we have a non-Russian speaking participant. Okay, good. So thank you very much for attending the seminar. Unfortunately, I don't see who is in the offline part of the audience, but anyway, good evening to everyone. So before I explain any of those sophisticated terms that you see in the title, let me start with a very, very, very known example for everyone that have ever attended high school. So we start with a quadratic polynomial in one variable x with complex coefficients. And then if I ask you for which values of those coefficients, b0, b1, b2, this polynomial has a multiple root, then, well, most likely you will answer that...
Арина, прошу прощения, секундочку. Боря, если вы слышите, включите, пожалуйста, запись.
Я включил, да.
Ага, потому что у нас в трансляцию звук почему-то не идет.
Угу.
Хорошо. Угу.
Okay. I can continue, right? So at least everyone in the room hears me. That's... Sorry, can anyone hear me?
Yes.
Oh, good, thank you. Okay, so that happens whenever some expression known from high school, b1 squared minus 4b0 b2 equals to 0. And in other words, what we do, we choose a set 0, 1, 2 in Z, and then we consider the space, which I denote CA, of polynomials with complex coefficients such that the degrees of their monomials are included to this set. And since polynomials are uniquely defined by the tuples of monomials, we can basically identify, in this case, CA with a three-dimensional space. And then in this three-dimensional space, what we would refer to as the classical discriminant is actually the hypersurface given by this polynomial in the variables which are coefficients of polynomials in CA, such that for like any point lying on this hypersurface, actually like the corresponding polynomial will have a multiple root. So we can even speak of that more generally. We can consider an arbitrary set in Z and consider the space of all polynomials such that the degrees of the monomials are in the set A. And then we can ask ourselves, like, what is the hypersurface containing all polynomials that have a non-zero multiple root? And I emphasize that we're interested in non-zero multiple roots because, for example, imagine if your set A is consists of like some large positive numbers, then, well, of course, all the polynomials in the space CA will have a multiple root 0, which is not very interesting. So, and that's what we would call the classical discriminant, as opposed to the Morse discriminant that we will discuss slightly later in the talk. I can also say that, for example, this discriminant can be, of course, defined in a similar way for arbitrary set of larger dimension. And then in that case, we would talk about multivariate polynomials that vanish at some point together with all of their partial derivatives. But since I want to keep the talk as elementary as possible, most of the time we will only touch one-dimensional case, or like the case of polynomials in one variable. That's already good enough and still allows to draw pictures. So another thing that you can sort of realize that it's pretty hard, algorithmically speaking, to / impossible, maybe nonsensical at least, try to compute the discriminant explicitly for like some big complicated set A. So in one-dimensional case, so in case when A is in one-dimensional lattice, actually, one could use the following trick. We could remember that we have quite a related notion, which is called resultant. And so in this setting, since everything is one-dimensional, so suppose we consider a pair of polynomials in one variable, f and g, and then actually the resultant would be a polynomial in the variables b, I, c, j, such that it vanishes whenever the corresponding tuple of polynomials has a root. So one can compute this polynomial explicitly using Sylvester formula. So basically, this polynomial will be some large determinant. Large here is k plus m times k plus m, where k and m are degrees of, say, polynomials f and g. So this matrix is composed of the coefficients bi, cj's. So everything is pretty explicit. But, well, the larger the degrees, the bigger this matrix is, and the harder it is to just like give you like all monomials and the coefficients of all monomials in the resultant. But anyway, this approach can be actually used to compute the discriminant in one-dimensional case. For example, if you plug in the expression for the resultant, you plug in your polynomial together with its derivative with respect to the variable, right? Like we have one variable only. Then, yeah, like you will get an expression which is almost what you want. So almost the discriminant, as say in the case that it's very familiar to us. Well, but it's going to be times some monomial factor, which is the coefficient of the lowest term in some degree times the coefficient of the highest term in some degree. That's always going to be the case. Which degrees actually depends on the set A, as we will see later. Well, in multivariate case, well, kind of a more general result is true. It's going to be that, so there is a notion of resultant in multidimensional case, and there we can plug in polynomial with all of its partial derivatives, and then we would get something which is called a determinant, and it's equal to the a discriminant times some parasitic multiples in the product. But we are not going to talk about that today. Okay, so at least you can agree at this point that computing stuff explicitly probably is not a good idea if you want to learn something about this polynomials about resultant and the discriminant. And maybe in order to get something, we'll have to sacrifice something. And this something, well, it's going to be some extra information. To give you like an impression, so suppose you have a polynomial in one variable, which is like something like very large, written on the screen, yeah, occupying all the space on the screen, with some super large degree, with very, very nasty coefficients. And then, well, at least if you stare at this and you want to understand something about it, you still would try to understand what degree this polynomial is. And that at least will give you an information, for example, of how many roots it's expected to have or something like that. So a multi-dimensional version of this is the notion of Newton polytopes. And let me show you an example so that you understand what it is. So now what you hopefully see on the slide is a polynomial in two variables. And actually, it's in general, we will talk about low-round polynomials. So some degrees or degrees of the monomials are allowed to be negative as well. So what I can do next, I can take integer lattice, which has the same dimension as the number of monomials. And on that lattice, I can mark the points for every of the monomials present in my polynomial. I can mark the corresponding degree of the monomial. So for example, for this free term 5, which has the variables x1, x2 in degree 0, 0, corresponds to point 0, 0, and say for the monomial where x1 inverse x2 squared, it's the point -1, 2. So we do this for all of the monomials in our polynomial, and we get a finite set, which we call the support. And then if we take the convex hull of the support, we will get what we call the Newton polytope of our polynomial, or in this case, Newton polygon, since it's the case of 2 dimensions. So dimension 2, sorry. So as you see passing from the polynomial to its Newton polytope.
Sorry, Arina.
Yes? Yes?
Where is... yeah, I see. Okay, sorry.
Okay. So as you see, passing from the polynomial to its Newton polytope means sacrificing quite a lot of information. First of all, we lose all the information about the coefficients. Secondly, we lose all the information about the presence of monomials such that the corresponding point is present, is contained inside the convex hull of the support. So all we actually remember are what we call the degrees of leading monomials, so the ones that correspond to the vertices of the Newton polytope. That's everything that we remember. But as I will try to convince you later, this information already would give something about the variety given by the polynomial or system of polynomials or whatever. So before I do that, let me recall that Newton polytopes behave very well with respect to multiplications of polynomials. Every special cases, for example, if you multiply your polynomial by some monomial factor, that doesn't change your polytope in any way, except that it just shifts it in the plane or like in the space. A more general example of this, or like more general formulation of this phenomenon can be formulated in terms of Minkowski sums. Suppose we have a pair of convex bodies in Rn. We can define their Minkowski sum, which is the set of the sums a plus b with a and a, b and b. And it's going to be a convex body for if we take a sum of convex bodies. Let me show an example. Basically, every time we will talk about Minkowski sums and other interesting things, we will mostly mean that those convex bodies are polytopes. Also, most likely lattice polytopes, but let's come back to that later. But suppose we have these two bodies and let's compute their Minkowski sum. So it's pretty easy. We just basically take one of the sets, the second set, put it in some paint and then start applying it to like all points of the first set. And then what we will get is a convex body convex polytope if it's the sum of two polytopes, which is A plus B. And probably quite an essential thing that one can think of is that the Newton polytope of the product of two polynomials is equal to Minkowski sum of the Newton polytopes of those polynomials. But beware, it's not true for support sets. Take, for instance, the polynomial x squared minus 1. And then, well, it's on one hand, it's a product of x minus 1 times x plus 1. But at the same time, well, its support is 0, 2, while the Minkowski sum of the supports of those multiples is 0, 1, 2. So these guys don't coincide. But for Newton polytopes, it's true. Okay, so now an important theorem that I will explain later requires understanding the notion of the mixed volume. So the mixed volume is going to be a function that will take as an input a tuple of n polytopes in Rn. And that function is uniquely defined by a list of properties that I will show in a second. So first of all, if I plug in n times the same body A, then the value at such a tuple of the mixed volume is going to be just the volume of A. And here, before any disasters happen, I should warn you that when I say volume in all slides that follow, I mean lattice volume, normalized in such a way that the volume of a unit simplex is equal to 1. Unlike the usual volume where unit cube has the volume 1. So you will have to just multiply everything by n factorial, all the volumes. Another property is that the mixed volume is symmetric. So if you interchange arguments, then it's not going to change in any way. And finally, it's multilinear with respect to Minkowski addition. So for example, if you want to add a convex body to one of the arguments, and since it's symmetric, you just can consider without loss of genericity just the first argument, then you can write the mixed volume like as this linear combination. Okay, so now I can formulate, at least formulate naively, a very important theorem, which is basically the first thing that you want to explain anyone that you want in your research group if you do all this Newton polytope stuff. So we are talking about systems of n equations in n variables with given Newton polytopes. So each of the polynomials fi has its Newton polytope delta I. And provided that the coefficients of these polynomials are, well, in somewhat general position, and that I will explain slightly later. Just for now, think of it as, well, you pick randomly some polynomials such that with complex coefficients, such that they have the right Newton polytopes, and you want to compute their number of roots. So for this corresponding system of equations in n-dimensional algebraic torus, then actually the number of these roots is going to be the mixed volume of your polytopes delta 1, etc., delta n. So yes, it's a theorem that actually tells you that, well, the number of roots of a system of equations can compute it in terms of the Newton polytopes. So yes, we lose a lot of information passing from polynomials to polytopes, but some information we can still gain from that. So a very natural question, since we compute things in terms of the mixed volume, how can one compute mixed volume explicitly? So the answer is using polarization construction. So in case of n equal to 2, right? So we are just we are producing a bilinear form from the corresponding quadratic form, which is the volume. And well, the mixed volume, and in case of n equal to 2, that means mixed area, can be given by this, computed by this nice formula. So we have to, the mixed area of two bodies is the volume of their Minkowski sum minus the volumes of each of those bodies over 2. Here is a little example. Suppose we consider A and B some unit intervals, then their their Minkowski sum of those intervals is S square, a unit square. We already discussed that I'm talking about lattice volume, so it has lattice volume 2 because it can be presented as a union of two unit triangles. And then the mixed volume of this tuple AB is going to be 1, right? It's 2, the volume of this, minus 0, 0, because the volume of an interval in is equal to 0 over 2, and it's equal to 1. And it makes sense if you think of it in terms of Bernstein-Kushnirenko theorem, because if you consider a system of equations with these Newton polytopes, then the system will be linear, like one of the equations will be a linear equation on one variable, the other will be a linear equation for another variable, and then you solve them separately, and that's how you find the unique solution for such a system, typically, okay? So now I have to say a couple words about generistic conditions. So like what I mean generic. And in order to illustrate that, I want to provide the following pretty easy example. So I consider a system of equations where the first polynomial is just general polynomial of degree 2 in 2 variables, and the other polynomial is a general degree 1 polynomial in 2 variables. So if I want to compute their number of roots using Bernstein-Kushnirenko theorem, I get 2. And that makes sense, because if you intersect a conic and a line, that's what you will get. But of course, if you imagine intersecting a conic and a line, then of course there can be many, many outcomes. Typically, of course, it's going to have 2 points of intersection, and all of the coordinates of these points are going to be non-zero, which will give you 2 roots in the algebraic torus. What can happen is, for example, if your line turns out to be tangent to your conic at some point. This can be resolved actually by saying that you compute the roots with multiplicities, because in that case, it will be just one solution of multiplicity 2. So this is not the issue. The issue is another thing, namely, you can definitely, when you draw a conic and a line, draw them in such a way that, for example, one of the intersection points will have the coordinate y equal to 0. I mean, I'm pretty sure you can imagine that. And that means that this solution will be, for this particular system, will have a root which is outside of the algebraic torus, right? So it kind of runs away somewhere. But at the same time, one can track it down, because if you plug y equal to 0 in each of these 2 equations, then what you will get is actually a system in one variable, 2 equations in one variable x, right? So this system typically is not supposed to have roots, because a typical systems of 2 equations in one variable is not supposed to have common roots. But if the coefficients are such that the corresponding system belongs to the resultant, then that's the problem, right? And what are the coefficients of the systems? What are those polynomials? So in X. So, right, when you plug in y equal to 0, then all the monomials that contained y in a non-zero degree, they all die. So what is left are just the monomials that belong to these 2 edges. So such the corresponding points belong to these 2 edges, and the coefficients are as they were in the polynomial. So such a system will be called a truncation of your polynomial system FG that we started with. And yeah, so like if the root runs away, if the corresponding system has a solution, belongs to the resultant, then, well, you can first of all track it down, and second of all, you can understand what things should not happen, right? So to guarantee that the roots will stay inside the torus. And well, basically, the Bernstein-Kushnirienko theorem, if you think of it as the theorem that will guarantee you the certain amount of roots in the torus, actually is true for what we call Newton non-degenerate systems. So, well, basically these truncations on, like, let's say for now, parallel edges in this two-dimensional case should not have common roots. Okay?
But, sorry, there is one more option for degeneracy if the set of common roots is not discrete. For instance, in this case, if the conic is singular, consists of two lines, and the second line coincides with one of these.
Right. I didn't take that. Wait, but sure. Yeah. So, but I'm pretty, yes, you're right. But I'm pretty sure that you can still formulate it in terms of this, of the in terms of those truncated systems, I think. So, yeah. I don't know what I have to add here, but yeah, sorry. But at the same time, like such a thing, so like in the space of systems of equations with given Newton polytopes, the things that you described are probably of much higher codimension than one. So they are not going to create us any problems. But yeah, I mean, of course, my bad. I should have mentioned that as well. Okay, so I think I can go further, hopefully. So now we agree that we want, instead of the instead of computing the resultant and the discriminant, to compute their Newton polytopes. And for that, I need to remind some very important notion, which is the support function of the polytope or convex body in general. Because as you will see further, instead of the polytopes, we'll work mostly with their support functions. So suppose we have a convex polytope in Rn, then its support function is a function that takes as input a covector from the space dual to the one that contains your polytope. And as an output, it gives you the maximum that this function, which you can consider as a function on your polytope, attains on the polytope. Here's a little example. I take, say, a unit triangle in the plane. And then on the right, I actually draw like the linearity domains of the support function. Yes, so for the polytope, the support function is going to be piecewise linear. So let us kind of understand it slightly better. So suppose I take a covector, so on the right, that is kind of pointing somewhere like this direction. I hope like one can see the mouse. So that means that the first coordinate is slightly bigger, like bigger than the second coordinate, and they're both non-negative. Then, sorry, like no, the first one is not non-negative. Sorry. So that covector like that would attain the maximal value at the vertex 1, 0. And in order to find that value, you have to pair your covector with the corresponding vertex, right? So that's why you will get a linear expression 1 times x plus 0 times y for covectors pointing this direction. And say for a covector pointing this direction, the maximal value will be attained on the vertex 0, 1. And then again, if you pair it the covector with a function with a coordinate, then with a vertex, sorry, then you get 0 times x plus 1 times y. And well, for a covector pointing this direction, the maximal point is going to be 0, 0. Anyway, so we see the support function is piecewise linear. Its linearity domains are cones of maximal dimension that are in bijection with the vertices of the polytope. Moreover, if you know the vertices of the polytope, I mean, if you know their coordinates, you can describe the support function, because in each of the linearity domains, you know that it behaves but in a way prescribed by the coordinates of the vertex, has the same coefficients. And vice versa, if you know the support function, then you can find one by one each of the vertices of your polytope, and you know the polytope. Another thing is that if you take a random covector, then most likely it will attain its maximal value at one of the vertices. It's much harder to find a covector that will attain its maximal value at an entire edge or face of higher dimension. Okay, so another thing that I want to say about support function is that if your polytope lies in the space of strictly smaller dimension than the ambient space, which is the case for the resultant and the discriminant and the Morse discriminant as well, then all I said is true. Just I want to add here that all those all these linearity domains of the support function will have a common subspace of complementary dimension to the dimension of the polytope. So here they have all a common line. And that's, well, probably like, it's an important piece of information that we will need later. Okay, so now we come back to the question of how to compute the Newton polytope of the resultant. And let me show you the recipe. So we consider two polynomials f and g with supports a1, a2 in Z. So that means that the resultant, the polynomial that we are interested in, is a polynomial in the variables b, p, c, q, right? So in these b's and c's. And that's why the Newton polytope of the resultant lies in the space whose coordinates are actually indexed by each individual point of the set A and A1 and A2. So it lies in quite a big space. And what we want to do, we want to compute its support function. So the support function that would take a covector and give me the maximal value that this covector attains in the Newton polytope of the resultant. And the idea is, first of all, as follows. You take a covector, right? So then what you can do, you can consider this covector on what is not very best notation, but I think good enough to explain, the disjoint union of the sets A1, A2. How do you do that? So in this case, for example, when we have a support set with 2 points and support set with 3 points, our covector will have 5 coordinates. And then what I can do, I can just over each of the points, this one, this one, this one, this one, and this one, put a vertical stick of their height, which is equal to the corresponding coordinate of my covector, and then take the convex hull. And then what I will get is, well, some kind of a pair of unions of trapezoids, which are, well, which depend on gamma, for sure, which I denote N1 gamma, N2 gamma. Okay? I hope it's not very confusing. Okay, so first step, covector, this unions of trapezoids. Second step. So we can actually, since we are, so, you know, like computing the support function is basically trying to understand its linearity domains and the coefficients inside of each of the linearity domains. So in order to find those coefficients, in order to restore them, say for like, suppose you just have a linear function, right? And you want to understand its coefficients. So it's enough for you to actually evaluate this function on all the integer covectors, because, so well, that still gives you like infinitely many points. That is enough information to actually recover the coefficients of a linear function. So that's why you can think that this covector gamma has integer coordinates. And if that's the case, then what you can do, you can consider a curve parameterized by some parameter t, complex parameter t, where each of the components is of the form, well, some complex number plus t to the power, well, the height of the corresponding stick. So, right, so, or the corresponding coordinate of your covector. Then the next step is that if you plug this curve into your resultant, so basically resultant in, say this, in the framework of this example, is a polynomial in 5 variables, and we have 5 components of the curve. So we basically plug in every of these components instead of those coefficients, instead of those variables, and we get a polynomial, which is actually a polynomial in a variable t. Okay. Right. Another thing that we can do, our polynomials f and g are polynomials in one variable with coefficients b0, b1, c0, c1, c2. Okay. So again, we have 5 coefficients, and we can plug in like each of the components of the curve instead of those coefficients. And like this, what we get is something that can be viewed simultaneously as 2 different things. So on one hand, each of those polynomials can be viewed as a family of polynomials parameterized by this parameter t. These are polynomials in x, right? So like a family of polynomials in x parameterized by some parameter t. But at the same time, you can view the same expression as actually a polynomial in x and t. So it's a very important thing here, just like really kind of, I hope that this is clear, because we will pass from one interpretation to another and backwards. I hope it's clear. So then the next step is as follows. So when I took my curve and I plugged into the resultant, I got a polynomial in t, and it's quite easy to understand, and I hope I can leave it as an exercise for the audience, which can be done by an explicit computation, that this polynomial will have the degree, which is exactly the sought value of the support function rho on the covector gamma. Again, it's really easy. You just really probably need to do it by hand if it's like not very intuitively clear, at least. So that's true. So we need to find it, and we have this polynomial in one variable. So what can we do? Well, actually, we can remember that the degree of a polynomial is the number of its roots. Well, counted with multiplicity, right? But it's still the number of the roots. So if we, for this polynomial r of t, can find the number of roots, then we win. What are the roots of such a polynomial? Well, such polynomial, so like the number of roots of such a polynomial is the number of parameters t, such that the corresponding system from the family of systems in X, depending on that variable t, have a common root. And that happens precisely when these two guys viewed as, so like, okay, that happens, how many times does that happen? With multiplicities, it happens as many times as the corresponding system viewed as a system of 2 polynomials and 2 equations have a common root. Like, well, as many times as such a system has roots, sorry. The number of roots of a system of polynomials, 2 polynomials and 2 variables, has the, by Bierstein-Kushnirenko theorem, mixed volume of roots. Explicitly, one will have to take the volume of this Minkowski sum of the union of trapezoids minus each of them, volumes of each of them, and divide by 2. And then we get what we want. So for example, in this case, what we get is like if you take this covector and like this heights like this, I put just for convenience heights next to each of the sticks. Then if you take the Minkowski sum, then you will get a union of trapezoids with, again, those heights I put next so to the vertices. And then since the volume area of the union of a trapezoid is lattice volume trapezoid is just the sum of bases times the height, then one can just easily compute everything explicitly. And in this case, we will get some expression. So gamma 1 plus gamma 2 plus gamma 4. And well, this is a linear expression in the coordinates of gamma. In order to restore the corresponding vertex of the Newton polytope, we'll have to just take those coefficients, and they are going to be 1, 1, 0, 1, 0, because there is no gamma 3 and no gamma 5. So they go with coefficient 0. And that's how we restore the vertex of the Newton polytope. So this is whatever I say, is that it's not a new result. It's actually the result of Sturmfels of 1994. This result provides a combinatorial description of the vertices of the resultant, Newton polytope of the resultant. Sorry, I forgot the Newton polytope here. So basically, the idea is that one can just, for various sorts of gammas, construct those tens. I sometimes will call them tens. And then each of the tens and the Minkowski sums will be have different shape. So it's going to be a different union of different trapezoids. And then kind of enumerating all possible types of these shapes can describe one by one all the vertices of the Newton polytope one by one. And that's how we restore it. And also, together with the result about the vertices of the Newton polytope of the resultant, there was another nice result that actually the leading coefficients of the resultant, so the coefficients at the monomials corresponding to the vertices of the Newton polytope, as I said, are equal to plus or minus 1, and there was some algorithm to compute them. So before I move further, I of course have to say that that's not a good way to say this, so that leading coefficients are equal to plus or minus 1, because we defined the resultant as a polynomial that in the coefficients that vanishes whenever the corresponding tuple of polynomials has a root, right? But of course, if you multiply the resultant by any number, then of course, all the coefficients are going to change, but at the same time, this polynomial will still serve its purpose. It will vanish if you multiply by a non-zero number, of course. It will vanish whenever the corresponding system has a common root, right? So say the leading coefficients are not well defined in that sense, but what is well defined is that for any pair of coefficients at the vertices of the Newton polytope, one could compute their quotient. And then this quotient is already it's well defined. It doesn't depend on the scalar multiples. And this quotient is plus or minus 1, always. That's done by Sturmfels. And again, we are talking about leading coefficients. So all other coefficients, well, they're not plus minus 1 in that sense. And we are not talking about them. Anyway, so as I said, there was some kind of algorithmic approach to computing those signs, but actually there was no explicit closed form formula for this quotient for like a pair of two different vertices of the Newton polytope. And that's what we did in our joint paper with Alexander Estrov. And let me kind of give you a vague idea of how we did that. So now we are interested at quotient of coefficients at two different vertices of the Newton polytope of the resultant. So we can take a pair of covectors, again, with integer coefficients, as you will see later, that attain maximal value at one vertex and another vertex respectively. So like say gamma attains its maximal value at one vertex, sigma attains its maximal value at another vertex. And then the next step is we choose out of these two covectors, the one we like and the one we don't like, okay? So and then we can associate like corresponding tuple of polygons. So how do we do that? So again, like at the zero level, we have our support sets AI. What we have on top, it's the tent that we already know how to build from the covector gamma. So that's this union of trapezoids that's like just is, we take the, like we get put sticks of the heights coordinates of gamma, take the convex hull, and we get this union of trapezoids. But we don't only build tents this time, but we also make holes. We dig holes in the ground. And that's what we do with the covectors that we don't like, with the covector sigma. So these pictures are actually, well, they are the tents for sigma, but just reflected with respect to the horizontal line. Okay?
Arina?
Yes?
Is it true that by leading coefficients of the resultant, you mean the boundary points of
the ones corresponding to the vertex?
The ones
the
corresponding
vertices.
to the vertices, yeah.
Yes.
I see.
Okay, so that's how we get, so it's like basically, so these pictures are unions of tents, but like one is kind of is upward, the other is downward, okay? Okay, so now probably as you can guess, the next step is to again introduce new parameter t, but now we introduce it in this particular form. So each of the components of this curve, so this parameter t is non-zero, will be, well, t to the power coordinate of the covector we like, plus t to the power minus coordinate of covector we don't like. Then we get, well, some curve, which we call Khovansky curve. And then we plug it in again into the resultant. And what we get is actually a Laurent polynomial in T. And then, well, again, we can easily understand that the leading terms of this Laurent polynomials are actually going to be the sought leading coefficients, gamma and sigma, times, well, t to the power value of the support function at gamma. And here is minus value of the support function at sigma. So now, I can, as you can imagine, what happens is that we remember the famous classical Vieta formula that relates the product of roots of a polynomial with the quotient of its leading coefficients. And what we get actually is that this quotient of the leading coefficients, like highest and lowest, I mean, is equal to -1 to the power, the number of roots, as in the classical formula. And this we know that it's the mixed volume of these two polygons. So times the product of roots of this polynomial R of t. At the same time, again, passing from this interpretation where polynomials f and g, when you plug in coefficients depending on this new variable t, can be also viewed as systems of Laurent polynomials in two variables xt, we can realize that what we need to do is this, for this system of two polynomial equations in two variables to be able to find the product of the second coordinates of all of these roots, right? So these roots are going to be roots in the algebraic torus. And in the algebraic torus, we can, well, multiply things component-wise. But here, what we need to do is we take the product over all second coordinates of all the roots of this polynomial system into equations. And, well, we win if we can find an explicit expression for this product. Yes, so, and actually, this explicit expression, which unfortunately I probably won't be able to talk about in a lot of detail due to the time restrictions, can be computed using the multivariate Vieta formula that we have proved together with Alexander Esterov. So the idea is as follows. We kind of look at a slightly more general question. Suppose we have a system of two polynomial equations in two variables with given Newton polytopes and with an extra condition that this coefficients, the coefficients corresponding to the vertices of those Newton polytopes are equal to 1. Then what we do, we choose some point in Z2. So some point with integer coordinates. And what we want to find is the product over all the roots of this system of monomials x to the power xi1, t to the power xi2. So then
there was a question, what does it mean to developed?
Yes, so it's a good question. So what I want to like, it's some requirement on the position of the polytopes with respect to this vector, to this integer vector. But I just want to say that I don't want to speak about, I want to speak about it in detail, but for the case that we apply this theorem to, when we have those polytopes of the shape and this vector equal to 0, 1, this condition is satisfied. So yeah, I mean, I'm not talking about this. Moreover, I mean, of course, like together with the question, what is 2 developed, there should be a question, what is MV2? And again, that's not something I will tell, unfortunately, in detail. I just want to say that it's some analog of the mixed volume of polytopes, which takes values in the field of two elements. It depends on like a tuple of polytopes and like a vector. And it possesses several nice properties, like it's symmetric with respect to those polytopes, and it's multilinear with respect to Minkowski addition, but it cannot be restored from like for using any polarization construction, unlike the classical mixed volume that we discussed. But it has some completely different nature, and this function was in detail studied in our joint paper. So if you are interested in that, you can just look there. But we can explicitly compute this. Like there is a way to compute the mixed volume, the two mixed volume of a tuple of polytopes, and that's why in this case, when we apply it to the setting with the resultant, this product of like the product over here can be actually written down as the mixed two volume of the polygons N1 sigma gamma, gamma sigma, and 2 gamma sigma 0, 1, because we multiply t's. Okay. So yeah, so that's the operation that we could do for any pair of vertices of the Newton polytope of the resultant, and like that we can again restore all those quotients for leading coefficients of the resultant. Okay, that's all I wanted to say about the resultant. So unfortunately, I also don't have much time. So I have to pass on to the next step. So one thing that I still want to say is that one could probably think that the same method can be applied to the case when we compute the Newton polytope of the discriminant. So there we would have a covector gamma, which is parameterized by the point of some fixed support set A. And then we could consider again, like using the same construction, a polynomial in two variables, xt, depending on gamma, of course. And we could, like, as the other polynomial, take its partial derivative with respect to x. And then we will get a system of equations with, since we are using logarithmic derivative that has the pair of the same Newton polytopes. And then we could actually try to use Bernstein-Kushnirenko theorem to compute its number of roots, and that would be what we want. But one has to take into account that actually this system is, the coefficients of the systems are not completely independent from each other, right? So like it's the partial derivative of this polynomial, right? So which creates some degeneracy, namely at this pairs of edges. But the good news is that, well, those roots that kind of escape the torus, they can be easily tracked down, and their contribution can be counted. And the good result is actually that this contribution, these coefficients, they do not depend on the shape of gamma. They depend only on the support set A. They depend on the distances from the leftmost point of the support set to like the closest point. And here, rightmost point to the closest point. That kind of actually is makes sense, because as we said from the very beginning, the Newton polytope of so the discriminant, the resultant in which we plug in the polynomial together with its derivative is equal to the discriminant times some monomial factor. And the degrees of the variables in this monomial factor are actually given to you basically by the geometry of the set A, not any kind of shapes of the roofs here. So now we can pass on to another discriminant that I haven't yet introduced, which is the Morse discriminant. So now we fix a finite set in one-dimensional lattice, but in my thesis, yes, sorry?
1 second, there is a question.
Maybe I have lost the point. If we are speaking about the leading coefficient of a monomial and next coefficient, if we substitute x plus 1 instead of x, we change this invariant. It is not an invariant.
Where do we plug x plus 1?
We want to know something about the possible amount of
the substitutions. Okay. But
yeah.
The substitutions we're talking about should not change the solution sets over the complex torus. But what you do is not pretty legal. So like what we are allowed to do is like monomial changes.
It's a rare case that by this substitution we one of our roots got some coordinate equals 0.
Well, I mean, yes, it can actually happen. So like if there was a common root, like, I don't know, -1, and then you do this thing, then actually the solution is outside of the torus after what you do. So don't do that.
If we replace one by some arbitrary number, it have it's a rare case that we lost a root.
Well, still, we just don't apply these translations of the variables. I mean, like I don't know how to answer to that question in a sophisticated way, but all the changes of variable that we are allowed to do in the setting are actually just invertible monomial changes of variables. So that's all I can say in this situation, but I don't know if anyone from the, I don't know. Yeah. Can I continue?
Yeah, please.
Yeah, so we fix a finite set in one-dimensional lattice. In the setting of the thesis at least, in detail, I speak about the case when A is equal to, well, integer, points from 1 to etc. n. So when we will speak about polynomials, general polynomials of given degree n. And what we're interested in is are the following strata in the space CA, which are of codimension 1, which we call caustic and Maxwell stratum. So caustic contains polynomials in the support in the space CA, so with support A, such that if you view them as function from the algebraic torus to C, then it has a degenerate critical point. So basically, at some point, the first and the second derivatives vanish. So another locus that we're interested in is the Maxwell stratum. And this contains the polynomials with support A, such that if you view them as maps, they have a pair of coinciding critical values taken at distinct points, like drawn here. And this actually, this setting, these pictures, they were inspired by the case of degree 4 polynomials, and we will discuss that case in more detail. But anyway,
sorry. So all this kind of question, if you speak about derivatives, it's they are not invariant with respect to multiplication by monomials. So when you solve equations, all the properties for Newton polytopes are translation invariant, but here is not. You're not.
Well, when I say partial derivative, I say this logarithmic one. So the one that I take partial derivative and then multiplied by x, and then I can't do anything.
But still, if you multiply a polynomial by a monomial in x, all critical points.
The zero. So again, even in the case, just generally speaking. So if I multiply my polynomial by some monomial, then solution sets in the torus doesn't change, right?
Yeah, but the critical point.
That's why.
Zero locus is preserved, but the critical points and the property of caustic, Maxwell stratum, everything is not invariant if you multiply a function by a monomial in x. So function. So if you take a function from your graph and multiply by x, and then it's not discriminant anymore.
If I take a function multiplied by x, then it's not what?
So you, for instance, you multiply by x the function which is on the right hand side of the graph. So the function has two critical points with the same critical values. So when you multiply by x, the values at those points will be different.
Yes, but if I multiply by x, then I get out of the space of polynomials with given degree. like
Just
I get out of the support
want to say
set.
that all these properties are not translation invariant.
Yes, they're not translation. Yes, they're not.
Okay, that's fine.
So wait, so that's your question.
So here
so your question implies that so like in the classical, so let's say for the classical discriminant, actually like the Newton polytope, like, so like the set A can be like freely moved in the say in Z, but yes, in this case it cannot. So like say if I translate the set, shift the set, then of course like all of this changes. Yes.
Okay, so do you solve? You consider still a torus, or do you?
No, I still consider the torus, but just yes for like this the translations of the same set. My Newton polytopes will be different, and actually the way they change is pretty fun.
Okay, thank you.
Yes. So I say that the polynomial is Morse, and probably that's not the best notation, but well, anyway, that's work in progress. Anyway, so maybe one day it will change. But I say that it's Morse if it doesn't belong to either caustic or the Maxwell stratum. And now let's look at the concrete example. We talk about degree 4 polynomials. And then if you want to compute the polynomials that define the caustic and the Maxwell stratum explicitly, in this case, one can easily do that. And the first polynomial defining the caustic, which I denote HC. Well, so these are actually the coefficients of like general coefficients of a polynomial of degree 4. So probably if you computed discriminants of cubic equations, you recognize the coefficients. And that's not a coincidence. As I said, we have to have the first so the first and the second derivative vanishing. So basically the polynomial defining caustic is discriminant. And that's why studying its Newton polytope is not very interesting, because it was already done by Gelfand, Kapranov, Zelevinsky. So that's not the challenge of the topic of this work. The challenge of this work is trying to understand what to do with Maxwell stratum, how to compute it. Well, algorithmically you can, but like the bigger the set A, the bigger the degree of polynomials, then the worse it becomes. So it's again like pretty nonsensical to try to compute it by hand. But at least a good question would be, say, what is the Newton polytope of polynomial defining it, or something like that. So, well, in this case we get some like lovely expression, but in general it looks pretty nasty pretty fast. So the problem that I solved within, say, like this thesis is as follows. So for A, which is the set of points from 1 to n, so when we talk about polynomials of given degree n, we want to describe the Newton polytope of the Morse discriminant, which I define as the following polynomial. So it's Maxwell, the polynomial defining the Maxwell stratum squared times caustic. Why I do that? So for now, let's just let me answer to this as its convenience. But later, hopefully, I will show you why I like to take Maxwell stratum squared, and why I still prefer to multiply it by caustic, even though the Newton polytope of caustic is well known. Okay, but for now, say in the case 1, 2, 3, 4, this polytope can be computed by just taking this product of polynomials on the previous slide, expanding it, finding the leading monomials, and you know, you're done. It's a pentagon in R4. Actually, the fact that it's a pentagon in R4, it's pretty logical. But I don't know, like I will answer to this question if I will answer to that if anyone in the audience wants to know. But anyway, so if you want me to describe the support function of this polytope, which I call Morse polytope, just slight abuse of notation, then of course I would say that I would just use the same old trick as we did before. So I would play with all sorts of covectors and consider those, so like build the tens over the support set A and take the convex hull and consider like polygons and gamma, and then try to kind of play with the same tricks I've shown you before. So in general, we start with a generic covector gamma in the space dual to the one that contains the polytope, which is RA star. Actually, and this wasn't asked by audience, but it's actually true. So it's actually enough to consider not only the covectors with integer coordinates, but also non-negative coordinates. And that's what I've been doing all along, but like it didn't cause any questions. The reason behind this is that actually, just as the discriminant, as the resultant, Morse discriminant is homogeneous in many, many nice ways. For example, if you rescale your variable or multiply all the coefficients of your polynomial by some number, then non-zero number, sorry, then that does not affect it being on the Morse discriminant. So that's why the polytope of the Newton polytope of the Morse discriminant actually lies in the ambient space of strictly higher dimension. And as I said, all the linearity domains of the support function have a common subspace. And well, actually just moving those coordinates of gamma along this common subspace will actually let me obtain a covector gamma in the same linearity domain with non-negative integer coefficients. And that's why I need to consider all different gammas with non-negative integer coefficients. But then for such gamma, I can do the same trick. I can consider a family of polynomials parameterized by a new parameter t with coefficients of the form, well, qp plus vp times t to the power, the coordinate of this covector. And the Newton polygon of such polynomial, if viewed as a polynomial in two variables, is actually going to be, again, this same old tent that I've been talking about before. And then the idea is that if you plug these coefficients in the Morse discriminant, which is defined by a polynomial whose variables are those coefficients, you get, again, a polynomial in T, and the degree of this polynomial is the sought value of the support function of the Morse polytope on gamma. So again, by the same thought that the degree of the polynomial can be found as the number of its roots, one can actually reduce the problem to the following one. So for like all sorts of like those families, depending on the covector gamma, for how many complex values of T is the corresponding representative of the family non-Morse. Again, that's still the same part, like the same thought, the same interpretation as was for discriminant and for the resultant, if you think of that. But then here it's like there we were using Bernstein-Kushnirenko theorem or Vieta theorem or whatever other like easy things. So in this case, it's pretty not clear how to proceed. So the key idea here is as follows, but before I show you the picture again, I just want to say that on the next slide, since we can kind of solve the same problem for all various gammas, we can just kind of think that we fixed a gamma and are solving problem for it. And then, we will repeat. So that's why we'll drop gamma from all the notations, but just remember that it's like a local question for each individual gamma. Here, gamma is fixed. So what we can do is the following thing. First of all, we start by the idea of, introducing one more variable. I mean, we introduced only one variable t, why not introduce one more? And what we do, we consider a space, so like a hypersurface defined by this equation, ftx minus y equal to 0. But if you think of that, it contains the point tx, t, and ftx. So like we kind of, for points xt, we remember the value of the polynomial ftx at the point x. And we put it in this new variable y. That's why we introduce it. So that's a hypersurface in three-dimensional space. Then the next step is what we can do. We can introduce a projection that forgets the coordinate x. Again, why not? And we can consider the restriction of this projection on the hypersurface H. Then the critical points of this restriction are going to be precisely the points where the polynomial defining H and its partial derivative with respect to x vanish. They define a spatial curve C, which is drawn like poetically in this picture in dark blue. I hope it's visible. Now, the critical values of this projection are, well, the projections of critical points. So this, they compose a curve D. So the curve D is a plane curve, right? And the coordinates YT, like in the torus with coordinates YT. And actually, due to the choice of the set A, so A was the points 1, 2, etc. n, due to the fact for such that for such a set A, a generic point on the Morse discriminant is the one. So like a generic point on the Morse discriminant corresponds to a polynomial that either belongs to the caustic, where the first and the second derivative precisely vanish and nothing more, or belongs to the Maxwell stratum and it has a strictly one pair of two critical values attained at the same coinciding critical values attained at different points, at a pair of two different points. We can actually say that this curve D is going to be a singular curve with only nodes and cusps as singularities. And then one can actually interpret the nodes and cusps of this curve D as follows. So cusps are going to be precisely the points of the form y0, t0 on the curve D, such that if you plug them in your polynomial, then you get a polynomial in X that has exactly one root of multiplicity 3. So the number of these cusps would actually tell you how many polynomials of the family ftx belong to the caustic. And that's an important part. I mean, we need to track those, like, because that will help us to find the value of the support function. While the number of nodes, which are the points y0, t0, such that when you plug them into the equation, you get a polynomial in X that has two roots of multiplicity 2. So the number of these nodes actually correspond to the number of polynomials in the family ftx that get on the Maxwell stratum. And in order to find the sought support function of the polytope, of the Morse polytope, the way it was defined, we took Maxwell stratum squared times caustic. What we have to compute is twice the number of nodes of this curve D plus the number of cusps of the curve D. And that's what we do. So we reduce the problem of computing for every single gamma. We just like kind of do the same trick, like to create the same picture. And then what we have to do is for the corresponding curve D to just compute twice the number of nodes plus the number of cusps. And then a tautology is that we can rewrite it as twice the total number of singular points of D, like nodes and cusps, minus the number of cusps. I mean, here I did nothing. But the nice thing here is that, as I said, cusps correspond to the number of cusps is the support function of the caustic. of the Newton polytope of the polynomial defined in the Gauss. And these guys described due to Gelfand-Kapranov-Zelevinsky. And well, the method that I also mentioned briefly before starting to talk about Morse discriminant. So in this case, depending on this covector gamma, actually the number of cusps is equal to the area of this union of trapezoids of the stent minus gamma of like the first and the last coordinates of the covector gamma. Okay, so what we actually did, we reduced the initial problem to computing the number of cusps and nodes of the curve D. So that's what we will have to do further. Here's a little reminder of what polytopes we are working with. So this is this polytope N gamma. So that's the 10th. And then if we add this new variable and consider the polynomial f t x minus y so then its Newton polytope is a pyramid with the base, which is the same 10th, n. But since we added an extra monomial y, then that kind of gives you an extra vertex outside of that plane. So the Newton polytope is going to be this pyramid. And that's what we call delta. Okay, so now, again, I hope that it's clear what we reduce our problem to. We reduced it for a spatial curve C and its projection D. We reduced the problem of like computing whatever we need to finding the number of nodes and cusps of the curve D. Okay. So now another thing is that we can actually treat this as like kind of look at this as like a slightly an instance of a more general question. So we can just take a finite set in Z3, which I call A tilde to not confuse with A. I can take delta, which is convex hull of A. And I can consider a curve given by generic polynomials with support A tilde. Then I can consider the projection for getting one of the coordinates, say coordinate X, and consider a curve, which will be the projection of my complete intersection C in the plane. So it's going to be an algebraic curve with isolated singularities. And then the question that I can ask is, what is the sum of delta invariance of the singularities in torus, inside the torus? For those that are not familiar with what delta invariant is, I want to just say that, for example, if you, for the given support set A, you know that, say, all singularities are going to be nodes and cusps, then the sum of delta invariance actually will give you this number of nodes and cusps. So we can just think of it as this, or you can, in this general setting, you can think, okay, like if all the singularities are nodes of this curve D, then what I'm looking for is the number of those nodes, okay?
So, sorry, you said that the F1 and F2 are generic. It means that this projection will not have other singularities as double points as nodes. There will be no cusps.
The thing is, actually, even if they are generic, so the curve D might have also, like, depending on the set A, the curve D might have some monsters as singularities. So, for example, imagine that, well, I don't know what, okay. So this can, for example, happen if you consider some, I don't know, like maybe some kind of pyramid as Newton polytope, but then I'm talking about support sets. So from the integer points of the support set, just remove all that are standing from the base at the distance 1. Just remove them. And then that's already going to give you some problems. in general. But so the classification of like what kind of singularities can occur, if so, like when not all of them are nodes, and if not nodes, then what? That's actually like a little spoiler, like some work in progress that we are writing now with Sasha and Zhenya Statnik. That's some completely different question, and like which definitely lies outside of this thesis, but it's a very interesting question. Like, what kind of singularities can happen even for generic set, even for like deltas that like, so like the set A that like generate lattice and like many good ways and so on. So still bad things can happen, not only nodes as singularities. Okay.
Maybe.
I mean, I hope we'll finish that paper and then I will be able to tell you more. But here is a little explanation of what actually makes this problem easy and hard at the same time. So for this, I want to consider the set A tilde, which is just the integer points of size D simplex in Z3. Then the curve D, in this case, will be a plane curve of degree D squared with only nodes and singularities. That's true, like for generic like polynomials with support A tilde, that's going to be true. And then actually, if that's true, then what one can do, one can pass to a good toric compactification, which in this case is basically CP3 and CP2 respectively. Well, what one can do is one can like complete the curve C by adding points at infinity, and then consider the map, this projection as the map from this completed curve C to CP2, and use the double point formula in terms of characteristic classes of the map F to find the number of nodes. And of course, I messed up with notation here. It should have been 2A1. I'm sorry. So then if you use this formula in our case, then what you get is, again, I messed up. I'm sorry. That the number of nodes will be d squared times d minus 1 squared over 2. So probably you might think, I mean, especially, of course, I guess this is addressed to more specialists than just the rest of the audience. I'm sorry. But you might think that, okay, like nothing stops us from doing a similar thing in other cases. We can just pass to toric compactifications, like the like for the curve C, right? That's defined by the polytope delta, and say like for the curve D, we can find its Newton polytope and like consider the toric variety, toric surface associated with its Newton polytope. And then we could like kind of use the same things, because like computations and characteristic classes is like can generalize to other toric varieties, not only projective space. But unfortunately, there is something that we took for granted, but actually, which is definitely not true in general. What we took for granted is that the curve D is, well, Newton non-degenerate. I didn't explain properly what it is, but in this case, it means that this curve D in the projective plane intersects the orbits, so like these one-dimensional orbits, the lines in projective planes, transversally at like d squared points, d squared distinct points in general. So we used this, we took it for granted. We used it in this computation actually when we were computing this term. In general, that's not true. So for other support sets, that's not true. And what can happen is that on the infinity, so like on the one-dimensional orbits of the toric variety associated with the Newton polygon of the curve D, oh, okay. So, yeah, so congratulations and just enjoy. So, like, yeah, on this one-dimensional orbits of the toric variety associated with the Newton polytope of D, what we will get is some kind of monsters, some singularities that are significantly more complicated than the singularities we started with. I mean, we wanted to compute some nodes, and then suddenly what we end up with in best case scenario, trust me, is some singularity which looks like, well, like some kind of smooth branches transversely intersecting this orbit at some point. Well, at some point. But then, of course, to understand this singularity, to understand its input in the, well, if you want, like into early characteristic of the corresponding plane curve D, one has to, for example, determine how these branches intersect each other. So just information that they transversely intersect this orbit is not enough. But anyway, good news is that all these monsters at infinity that spoiled the picture and like that are more complicated than the singularities we want to study, like nodes and cusps. In my work that recently appeared in Mathematische Zeitschrift, I was able to reduce them to quite a nice family of singularities, which are called forking path singularities. And again, since I don't have much time, all I want to say is that I can illustrate and give you like an example where exactly this singularity with these four branches intersecting in this nice way appears, okay? So yeah, so the setting is as follows. I consider the support A tilde with these points, which I marked red in the picture. So the Newton polytope is going to be just some simplex. Okay, then what I want to say is that I take, like, of course, F1, F2 generic with this support, and I want to compute the projection D of this complete intersection. That's still true. So now I want to understand how the curve C intersects the orbit of the toric variety associated with this polytope delta at the two-dimensional orbit associated with this phase gamma. I know that I am saying quite a lot of words, so like for the rest of the audience, if there's so I just want to say that let's consider what happens like in this case. So we have like three coordinates x, y, t. I want to consider the plane xt, so y equal to 0. And what I want to understand is how the curve C, defined by generic tuple of polynomials with this support, intersects this plane. That's the smart words I was saying. So in order to do that, you basically have to substitute y equal to 0. And you get a system of two equations in x and t with Newton polytope, which is this triangle. And the number of the solutions of the system is going to be the volume, according to Bernstein-Kushnirenko, of this triangle. So it's going to be 4. So moreover, one can actually note that if you project all these 4 points, forgetting the coordinate x, then they will get mapped onto the single point D. So that just follows from the form of this system, like when there are monomials like that. then, so the situation is that, okay, we have like 4 smooth branches of the curve C. So it's since F and F1 and F2 are generic, so they intersect this plane transversally, smoothly, nicely at this point. But then when you project, then you can get a curve D with like this 4 branches passing through the single point. And in order to understand what kind of singularity you obtain here, you really need to know the information of how these smooth branches intersect each other. Like, do they intersect each other transversely or not, or whatever. So good news, which like follow from like the computation that I did in my paper, and that's like pretty non-trivial. So good news is that if all this information, like about the type of the singularity, I can capture from the picture on the left. So how do I do that? I start with this facet, gamma. I call it gamma. I didn't put notation gamma, I'm sorry, but like it's a facet. So I forget all the coordinates of the points of my support set, except
may I ask you,
yes.
Are there other integer points at this simplex?
Well, so in this one, in the setting of this example, no, only these 3.
Okay.
But of course, if there were, then it would influence the computation that I will talk about next.
You start with certain finite set, then you take the Newton polytope, and then you add all other integer points in the same Newton polytope.
No, I don't add. No.
So there are some integer points which are not included to the support.
Yes.
Okay.
Yes.
For instance, 111. 111.
Yes. And actually, that's the beauty of the thing, that the singularities at infinity, they don't depend only on the Newton polytope. So not only on the convex hull, but actually on the monomials that are present.
Yeah.
So let me show, what I do next. So I on all the points of my support set that got onto this facet, for example, here it's 400, 000, and 001. I forget the second and the third coordinates. So what I get is the set 04. The set 04 generates index 4 sublattice in Z. And I remember this information. Then what I start doing, I start tracing planes which are parallel to this facet at like distance, integer distances from this facet. So like I trace like at a distance 1, like a facet here, so a hyperplane here, parallel to this facet. And maybe I encounter a point. So like in this case, I was lucky and I encountered a point of the support set. Then I repeat this, so I forget the coordinates of the points that I encountered so far. So the second and the third coordinate, and I get 0, 2, 4. And then this generates a lattice of index 2 in Z. Then I continue, I do one step further, and again, I was lucky. I was choosing this example, like not for nothing. And I encounter another point of my support set at the height 1. And then again, I do 0, 1, 2, 4. I generate the entire lattice. After that, if I continue adding new points, then nothing will change because I already I already generated the full lattice. But what I get is this sequence. So like for this facet, blue facet, I can, I obtained a sequence of numbers which stabilize at 1. Well, the forms like here it was 4, 2, 1, blah, blah, blah. And then actually using this sequence, I can determine the type of the singularity. So I can actually, looking at the sequence, I don't want to explain how, but I can know that there are 4 branches divided into two groups, such that the branch from one group and the branch from another group intersect transversely, while 2 branches from the same group intersect with order of contact 2. And this information is enough for me to reconstruct the singularity, or for example, to compute the early characteristic of its Milnor fiber. That's already enough to use in all my computations. And this is this nice formula. So as you see, if my support set A generates the, if my support set A, if the first coordinates of all the points of my support set A generate the lattice Z, and then this sequence for like this facet and like all other facets, of course, they stabilize at 1, and therefore in the formula for early characteristic of the Milnor fiber of S, the sum actually is finite, because starting with some element, all of these summands will have no contribution. So in this case, for say this singularity, we using this formula compute that actually it's the early characteristic of the Milnor fiber of it is equal to -12. So in order to study all those singularities at infinity, whatever that means, I hope it's like kind of at least vaguely clear, the idea. I just do the same procedure for all non-horizontal facets of the polytope delta. And I get those sequences, and I can say how many points, how many singularities are there, and what's their type, and what's their contribution to the early characteristic of the curve D. And that leads to the result that I obtained in the paper I mentioned. So it was obtained in a larger generality than just C3. So it was so for like a curve in complete intersection curve in Cn+2, and then I project for getting n first coordinates to get a planar curve, and then I was computing the sum of delta invariants of that curve. So I got that it's equal to 1/2 of this large expression. So where, okay, these guys actually, those are like the contributions of the singularities at infinity, like with this sequences I gamma for all non-horizontal facets of the polytope delta. Here is the sum of areas of horizontal facets. They play a different role in the story. Here's twice the volume of delta, well, also computable. And this guy we didn't meet, just treat it as a black box. It's just the Newton polytope of the curve D. It's the Minkowski, so it's the Minkowski integral of polytope delta with respect to P, which was proved to be the Newton polytope of the curve D, and that follows from the work, in particular of Alexander Esterov and Askol Khovansky about the elimination theory of Newton polytopes. So anyway, just we got this formula, and as you can guess, the next step is to apply this formula to our case when we consider this polytope delta and, well, like the support set, which which is obtained taking the graph of the covector gamma. And see, as you can see, so like this graph of the covector gamma might have some points which will not get to the convex hull of the tent, if you know what I mean. But then in the setting of this theorem, of this computation and so on, those points also matter, and that's what makes that's another difference between finding Newton polytope of the Morse discriminant from finding Newton polytope of classical objects like discriminant or resultant. So so basically, we would have to deal with all sorts of those sequences I gamma for facets of the polytope delta, which is this pyramid. And I can reformulate this combinatorial data in terms even of like of the planar picture here, that's even better. So the idea is as follows: when you drew this tent for the covector gamma, you obtained some polytope, and then if you project this polytope onto the plane, then you would get a subdivision of an interval, and the vertices of this subdivision are going to be precisely the points such that the point hanging over them is a vertex of this union of trapezoids. And this subsets I denote by W, like in my work, for example. So that's just a subdivision. And the subdivision is part of the combinatorial information describing the vertices of the Newton polytope of the discriminant. So that's a familiar thing. So now those sequences I gamma, I can, well, the equivalent information that I can gather is as follows. So like what I do for each of those vertical, so each of those top edges of this tent, I can start tracing lines parallel to them and then just record the order in which I obtain the points of the graph of the covector gamma. Like all the points except for these two that I started with. And then in the setting of this example, when I had like the subdivision W, W1, W2, W3, and then some point M, which was unlucky one, that such that the corresponding point, the coordinate of gamma is too small for it to participate in the roof. Well, as you can see from this picture, it does matter. Like unlike the setting of like classical setting. So like for such an interval, I can just define the sequence. So I record like, so I first encountered this point, so it's W2, then I encounter this point, it's like this point M, and then I encounter this point, so it's W3. And then I do the same for this interval, and all those top intervals of the tent. And that's basically the two pieces of combinatorial information that I will need to recover the support function of the Newton polytope of the Morse discriminant. So for example, if A is equal to 1, 2, 3, 4, and I consider a covector such that the roof has this nice shape, then in order to determine to which vertex of the Newton polytope of the Morse discriminant it corresponds, I have to look at like the subdivision. So the subdivision will be 1, 2, 4, because the vertices will be like when we project the correspondence that these are going to be the vertices of the subdivision. And then we also have to record the sequences, like for each of these two intervals, I will have to trace parallel lines to them and see how I encounter the rest of these 2 points. So like for this interval, I first encounter point 3, then point 4. And for this interval, I first encounter point 3 and then point 1. And that's basically what I remember. And using this data, I, well, plug it into some scary long formula, which I obtained, which basically is a consequence of this computation, up to some words that I didn't say. And I get that the corresponding vertex of the Newton polytope of the Morse discriminant is 0.0523. And then, well, here, this is a picture showing different shapes of covectors gamma that yield all the 5 vertices of this pentagon in R4, which is the Newton polytope of the Morse discriminant for degree 4 polynomials. And yeah, you can see here that say these two representatives, they kind of have the same shape of the roof, but they have different sequences of how we encounter points, because for this interval, when we trace parallel lines to it, we first encounter this point and then this point, while here we first encounter this point and then this point. That's what makes these two cases different. So yeah, I mean, that's, so like one last thing is that if why I took Maxwell stratum squared was the reason was that basically I just didn't want to divide by 2, like in this formula. That's the reason. And why I preferred to add the Newton polytope of the caustic. So the only reason is that I still hope to understand more about the combinatorics of this polytope of the Morse discriminant. Actually, when you take Minkowski sums with something, then this combinatorics kind of simplifies slightly, because less of the different combinatorial types of those covectors mapped to the same vertex. And that's why I prefer to just like add something I know to the Minkowski sum, so that like not too many vertices are glued. So not too many cones, realizing the same combinatorial data are glued into the same vertex. That's basically the only reason why I do that. But all of the methods I used actually can be tailored to just computing, say, the Newton polytope of the Maxwell stratum, if you want that. It's just going to be, going to have 3 vertices in the setting, and like too many different types of cones will yield the same vertex. And that's pretty hard to investigate. Okay, so the last thing I want to say is that this talk is based mostly on the 2 papers. So one of them is my joint work with Alexander Esterov, which is in geometric and functional analysis. And the other one is my work that's got recently published in Mathematische Zeitschrift. Please don't mind different surnames, that's my maiden name. And if you want to know more about what I was able to compute about Morse discriminant in more generality, then you can look in my preprint. But it's just outside of this thesis. It's just, but like, if you're just interested, you can just look at it. But I didn't rely on that. So yeah, thank you very much, and I will be glad to answer to your questions.
Okay, I have a question. So
yes.
Let me ask a general question. So the machinery of Newton polytopes is intended to help solving generic algebraic equations. So in your particular case, when you're computing the polytope of the discriminant, the corresponding polynomial is not generic, it's just very particular polynomial, the discriminant. If you consider other polynomials with the same support, they behave quite differently. For instance, all discriminants have non-isolated singularities, so they extremely different.
Sure.
So my question, what kind of information would you like to extract from this knowledge of the polytopes? Are you going to put them to some algebraic equations to solve some other problems, or whatever?
Well, so I understand your question. Actually, it's when it comes to applications, I'm not, So I personally am not gonna do anything with that piece of information. Because for me, like what encourages my interest in this combinatorial object is it's like, for me, it's mostly the combinatorics of the Newton polytope, say, of the discriminant, or in general, this a determinant. So like when you plug the polynomial and its partial derivative like into the resultant, because this polytope is like super beautiful, and like it's the secondary polytope, which like with some really beautiful combinatorics and like a lot of nice interesting questions regarding this polytope. And then like the Newton polytope of the discriminant, well, it's something even more interesting than that. So actually what really inspires me is not that I don't know, like for now, like I'm planning to do something with like knowing the Newton polytope of the Morse discriminant. Though, okay, like, one could think about that, but like, what inspires me is basically this, like kind of trying to develop a similar theory, like so about some other beautiful combinatorial object that would just be just like, I know, some polytope or something like that would have like as vertices like all sorts of combinatorial data or something like that, or another object more general than a polytope. So like that, I'm more motivated by the combinatorics and trying to kind of understand that kind of story. Another thing that motivates me there is that actually I didn't speak about this in this talk, and it's not the part of the thesis, but one can basically translate a lot of those, so like all of the things I said, all of those objects of this roofs. So like I can translate that in the tropical language, and then basically that means that I can come up with kind of tropical counterparts of those like of the notions of those like of different types of singularities. And well, that can kind of hopefully like encourage some kind of tropical methods and like singularity theory. So that's more that's what I'm more interested in, I guess. I don't know what else to add.
Yeah, that's hard because the type of singularity is not only determined by the shape of the Newton polytope. Yeah.
Yes, so like in the case of this, like say tropical lines, so yes, it's like it's extra information required. So not only the shape of it, but like other data similar to those like sequences of points, but like still you can using that data, so like kind of more refined notions in the tropical geometry, you can like still speak about stuff. So yes, it requires some kind of more refined in definitions and like more refined invariants concerning, say, tropical curves or tropical hypersurfaces or whatever.
Yeah, Arina, I also have a couple of questions. The first one is, what is the most complicated Morse polytope you are able to obtain using your methods?
What is the most complicated one, you mean?
How large are the examples you are able to compute explicitly?
Explicitly. So okay. So using using some algorithm that actually requires symmetric reduction. One, I was able, like on Mathematica, I'm not an expert in this. I mean, probably I'm not very good at like those computations, but like the algorithm I wrote, so like I was able to explicitly compute it up to like degree 12, I guess. Like, but I was only considering like just polynomials of given degree. I think degree 12, that was an overnight computation, and my computer just after that asked me not to experiment on it too much.
Yeah, and this polytope can also be computed using standard methods, standard algorithms in Mathematica, for example. Have you compared the results to those obtained by standard methods?
Wait, sorry, standard method is... So again, did I compare my results with like with what I obtained there? Yes, I did.
Yeah, and
so it gave the right.
They
match, of course. I mean,
great. More questions?
No, they match, and like that's yeah, there was something like one day I actually like did something for like, I don't know, degree 8 or something, and then for some reason like I lost like one of the vertices of the Newton, like, and I didn't sleep at night. I was feeling very bad. That was one of the lowest days, but then I found it was just right in front of my eyes.
Just a single night is not that bad.
I know. Yeah, but yeah, it makes sense. Yes, so that's very pleasant because, of course, like playing with all those roofs and computing things are like it's much faster than asking your computer to do symmetric reduction.
Okay, some more questions. There is one.
Sorry if it is a silly question. Either indeed some difference between calculating between the Newton polytope of the resultant and of the discriminant. I mean, if we take a polynomial with prescribed set A, take its derivative and calculate the corresponding resultant. Is it right that there exist leading coefficients that always vanish compared to the calculating the discriminant of a polynomial with prescribed a set and another polynomial that have an a set that same as the derivative of the first one?
I'm sorry, I probably didn't understand your question quite well.
Well,
I mean, you could try to ask it in Russian. That's also an option.
Так, если мы считаем выпуклую оболочку коэффициентов дискриминанта, то есть результанта многочлена и его производной. Правда ли, что она существенно отличается от выпуклой оболочки просто результанта многочлена с таким множеством А и другого многочлена, у которого...
С таким же множеством А. Ну, как бы, ну, просто в сеттинге, в котором вы сказали, то есть когда мы два разных полинома с...
Да,
ну, там, два разных полисадим.
Да, у второго ненулевые коэффициенты там же, где теоретически, где могут быть ненулевые коэффициенты у производной
ну, просто как бы немножко странно сравнивать эти выпуклые оболочки, потому что тогда у вас коэффициентов просто, ну, как бы типа вдвое больше получается. То есть как бы ну, то есть когда мы считаем... Сейчас, я просто немножко не очень понимаю.
Well, I think that Grisha asks whether the Newton polytope of the discriminant is the projection of the Newton, the natural projection of the Newton polytope of the resultant. Grisha, am I right?
Правда ли, что есть коэффициенты, которые тождественно нули у дискриминанта, но в принципе могут быть не нулевые у результанта?
In general, maybe, but not for the leading coefficients. So, in particular, for the leading coefficients, no unexpected cancellations may happen. So, the Newton polytope of the discriminant is just the projection of the Newton polytope of the resultant.
Thank you.
Thank you. Are there any other questions?
Yeah, some other question.
Yeah, Arina, you maybe
yes?
you said it at some point, but I probably missed it. That you compute the Newton polytope of this polynomial, which is h of the caustic, maybe squared times h of Maxwell.
No, Maxwell stratum squared times caustic. Yes.
You said something about it, but I missed it. Are you able to isolate the Newton polytope of the Maxwell part?
Yeah. I mean, I can.
Okay.
Yes, I can. Yes, I
Okay.
can compute explicitly the support function. It's just yeah. So like in the case when A is this saturated set, it's or actually even any A, I think. Yeah, so it's like changing the formulas like pretty slightly to move from one to the other, really.
Okay, I guess I missed why you prefer to compute this HCHM squared.
No, I probably said that, but like just so the squared part is only because I don't want to divide by 2. Just just why not? And I like to multiply by caustic only because this formula, the support function for the support function I obtained, basically kind of establishes a surjection between all possible combinatorial types of those kind of these roofs, like to the set of vertices. And of course, deep in my heart, I still hope to understand like this surjection, basically the preimages of this surjection or whatever. But then it's like pretty hard, like quite a lot of different types of those data. They actually are, when you plug it into the formula, you get the same vertex. And for the Newton polytope of the Maxwell stratum, that's like even like worse than that. So I was hoping that at least if I add the caustic, then at least I want to get the situation that two combinatorial types of those covectors with with different shapes of the roof, with different subdivision, and like all the rest is random, are not mapped into the same vertex. That would kind of simplify the study of the combinatorics. That's all.
Okay.
So it's basically a kind of convenience, just to kind of understand the polytope better. And like I was hoping that if I understand this Minkowski sum better, and then probably like when I talk about Minkowski difference from this something nicer minus the Newton polytope of the caustic, which I know, probably I would understand something yet. But like the spoiler alert, it didn't yet help too much. Still, there are a lot of more questions than answers.
Okay, thank you.
Thank you for the question.
Okay. Thank you, Arina. It was very nice, very clear talk. So I think that if from the formal point of view, the предзащита is successful.
Thank you.
Recording stopped.
Спасибо.
Вам спасибо за возможность тут предзащититься.
Все, всем спасибо. До следующего раза. До свидания.
До свидания.
вопрос. Вы случайно не знаете, предполагающий примерно помните тему знаете, куда с этим можно пытаться прикинуть? Потому что мы недавно сказали, что ставки на маркете нет, только куда разбираться.
Вот я ничего не могу сказать. А вы в Москве живете?
Ну, в принципе, да. Нет, ну, я бы не сказал, что меня в Москве что-то сильно держит, но про Новосиб я спрашиваю. Нет, ну, как бы, там, я не в своей квартире, так что если я из Новосиб, то я стал там, снял, это нулевая разница по деньгам. Или положительная. Да, ну,
не знаю, я так вот у меня ничего нет. В смысле, хотите в каком-то месте, чтобы заниматься профессионально этой темой?
Это или близко все-таки. Ну, я понимаю, что в точности это и не бывает. Там,
да.
Я смотрю, куда уходить.
Чтобы это можно было включить в эту самую профессиональную деятельность.
Да. Да.
Понятно, я так не могу сказать.
Понятно. Спасибо.